All right, welcome back. Algebra 1, Unit 2, Lesson 1. Today we're going to go over some vocabulary that's important to know when we get into the Unit 2 work. We're going to start with arithmetic sequence. We talked about sequential numbers before, 1, 2, 3, 4, 5. They just continue on, one right after another. And with an arithmetic sequence, the only difference is that they might not be separated by only that one. They could be separated by 3 or 5 or 100. And they don't always have to start at 1 or 0. So in this case, we're starting at 3 and we're continuing on by adding 2 to each one. The main thing you need to know about arithmetic sequence is that the difference between each consecutive or sequential term is that it's going to have the same number added to it. So in this case, it's a +2 in between in between the terms, in between the elements or the members. So between 3 and 5, it's +2. Between 5 and 7, it's +2. Between 7 and 9, it's +2. And then this ellipse here tells us that it will continue on forever and ever to infinity. All right, average rate of change is simply, in general, scientifically speaking, the average rate of change usually means the amount of change that something has divided by the time in which that it took that change to occur. So generally we use it for things like speed, the distance traveled over the time it took to travel that. But in algebra, it's a little more specific than that. We want to know specifically how much the y value or the vertical value changed over how much the x value or the horizontal value changed. So we have here something that shows us a triangle y over a triangle x. This triangle here, if you notice, it's not just a regular triangle. It looks kind of different, but when you see me draw it, it's going to look like a regular triangle. That is the symbol for the word change. So this is the math terminology, math symbol for the word change. So you might see this also as rise over run. It's change in y over change in x, or the vertical change over the horizontal change. So you pick 2 points on any graph. Here we have a point and a second point. And so it's the change in y. In this case, this is a 0.2 on the y, and this is a 0.1. So the change is 2 minus 1, or we went up 1 spot, so it's 1. Over the horizontal change, we went from here, it was 2 to 4, so it's 4 minus 2. So the bottom was 2. So our rate of change in this one is 0.5, or 1/2 between these two dots. Now, if you noticed, that graph that we were just looking at did not have a constant rate of change. You could have picked 2 different points on the graph and you would have gotten a different rate of change. A constant rate of change is when the rate of change does not vary, no matter what 2 points you choose. And we usually see this when we get into linear graphs or the graph of a line. So here we have a linear graph, and we've chosen here in red 2 points. The horizontal change is 2, the vertical change is 2, and the horizontal change is 1. So 2 over 1 reduces down to 2. And they did the same thing here, but we're going to pick 2 different points. Say we chose this point and this point. Let's look and see if we can find a difference here. These 1, 2, 3, 4 changes in the vertical, okay? Another way you could do that is you can choose one to be 0.1 and the other one to be 0.2. We'll call this 0.1, we'll call this 0.2. So you line it up, 0.1 starts with a 1 and 0.2 is a 3. So we're going to subtract them. So 1 minus -3, 1 plus 3. Because when you subtract a negative, it turns into a plus symbol. And so that's the same thing as this 4 here, right? So if you don't have a graph, you just have the numbers, you still have the ability to find the slope. Now, the horizontal change, 1, 2, or if we remember, this is 0.1, it's at 0, and this is 0.2, it's at -2. So 0 minus a -2 is going to be a +2. Now, 4 over 2, when we reduce it, becomes simply 2. Well, look at that. The 2 is the same as the change here and as well as the change here. So no matter what 2 points you choose on this line, your rate of change will be constant or unchanging. This is another way we call this is slope, and slope is usually written with an M. We'll get more into that later. But here's an example of a change that is not constant. So when they chose the red dot and this, I think that one's purple, it became vertical change 3 over horizontal change 1, rate of change of 3. But then when they chose this blue dot, it's a vertical change of 1 over a horizontal change of 1, resulting in a rate of change of 1. 3 and 1, those are two different numbers, so it's not a constant rate of change. The next terminology that we have here is continuous. And so that means if we have a bunch of dots, and then we're going to be able to connect them. I did not do a good job of connecting them, but they're connected with a line. I can draw this graph without lifting up my pen from the paper. That's continuous, okay? The next one that we have here is discrete. Now this one is not continuous. If I were to have a coordinate plane here and I just had some points on the graph but did not have any line connecting them, that would be discrete. So the information that I'm obtaining is going to be just what's in the dot and not what's in between. Okay, so let's see here. Here's some examples of continuous versus discrete data when you're collecting the data. Discrete has exact values. Continuous can be any value, because remember, continuous was we had several dots and lines connecting them, whereas discrete was just dots. So it doesn't go like this. You could have, if this was 0.1 and this was 0.2, you could have 1.735, etc., because it could be right there on the line. But here you could only have, if this was 1 and this was 2, it could only be 1 or 2. It couldn't be anything in between. Okay, so continuous is measured. So think temperatures, think milliliters, okay? Think pounds, whereas discrete is going to be counted. Items, how many items you have. I recently bought 4 plants. I didn't buy 4.5 plants. I bought 4 plants. I didn't buy 3.82. I bought 4. Okay, so measured, you see here, here's some examples with some of those decimals. Discrete here is going to be exact numbers. Continuous, think temperature. Discrete, think number of cats. Okay, so hopefully that is helpful to you. Domain, that means all the possible x values of a function. Now, I'm not sure we've gotten into what a function is just yet, but a function is going to be a mathematical equation where for every input you have, for every value you input to the variable, you're only going to get one output. So if I plug in the number 2 to an equation, I'm not going to get 7 answers. I'm only going to get 1 answer. Okay, so that's a function. So functions are kind of like machines. They do something with the input to get the output, so they change it in some way. All right, domain is all the possible values of that function that can go in. So some of the reasons you would have to limit it, and it couldn't be just all real numbers, is say you have something like 3 over x. Well, we know that x cannot be a 0. It can't be a radical. So there are certain things that we cannot input to this equation in order to have a possible answer. And so that will limit our domain, that will limit our values of x that we can input into that equation. Then you have end behaviors. When you saw me drawing a graph of a line previously, you can see that there's arrows here. The arrows indicate the end behaviors. It tells me what's going to happen to this graph as it keeps going. Well, it's going to keep going in whatever direction the arrows point. Most of the time when we talk about end behaviors, we're going to talk about something more like a parabola. This is a parabola that opens upward. Then you can have a parabola that opens downward. These are the end behaviors, okay? How it continues on off of the page, off of the graph. Function, okay, here we go. Function is a mathematical sentence that works like a machine. It takes its inputs, usually X, but doesn't have to be, puts them through a machine, which is the math sentence, and produces an output, which is usually Y. The one rule is for every input, there can only be one output. I think I have a picture here. All right, so usually when you see a function, instead of saying Y, it's going to say f of X. That's how you say this, f of X. X is the input. So f of, if we wanted to put in here f of 2, right? If we had a 2 there instead of the X, then you take this X and you put 2 and say 2 squared. So you could say f of 2 is 4, okay? So we input the 2 where the X's were. The function name, it doesn't have to be an F, it can be G of M, okay? Equals M to the 5th power, or whatever your function or machine is. But for every one thing you input, there can only be one output. And that's how you determine what a function is. The other way you can determine if you have a graph of the function, say something like that, you can take a straight line, a pen, and move it across the graph. And if it only crosses it at one spot, it is a function. So this graph that I just drew would be a function. However, something that's like a graph of a circle, if we had a straight line that went through that, it would cross the graph at 2 locations. So that one would not be a function. All right. Moving on. Inequality. So that's going to be a math sentence that uses a greater than or less than, or a variation of those, such as greater than or equal to, less than or equal to, in place of an equal sign. So 2x is greater than 5, okay? 3y is less than or equal to 2y plus 7, okay? So these are called inequalities, and there's some special rules that you have when you solve inequalities instead of equations. Interval notation. This is a way to write all the numbers included in a set. And usually we use this when we talk about domain and range. And so you're going to have either a bracket or a parentheses. And say something's going to go off to infinity. From infinity, say we had a domain of negative infinity to a positive 7. Okay, so it could be written something like this. You can never include infinity. This would mean inclusive, this is exclusive, and you can never include infinity. So it always gets a parentheses. However, the number 7, because of this symbol, tells us that it's included. If it was a one that wasn't included, we would use the other symbol there. Okay. Oh, here we go. Here's some examples. So we have A. When you have a solid dot, that means it is included. Okay. So it goes from A, which is included, all the way to positive infinity. This is our graph. So we have here, it's hard to see it, but this is a closed bracket around the A. And then infinity has the parentheses. Like I said, you can't contain infinity, so you have to use the parentheses for that one. This is the interval notation. Now you may already be familiar with set notation, and it's the set of x such that x is greater than or equal to a. That's how you'd read that in English. That's the English translation of this mathematical information right here. The set of x such that x is greater than or equal to a. All right, so this graph was closed and this one is open. That means that it's just going to be greater than. This one was greater than or equal to because it was a solid dot. This is a hollow dot. And so in this case, we are not including A itself, just everything greater than A. And so in this case, we had parentheses around A, and it continues on to positive infinity. And you can see the same goes when we have negative infinity. You just stick a negative in front of it, and it tells us which way the arrow is going to be pointing. It has nothing to do. This could be the number 127, which is positive. But the negative tells us that the arrow is pointing this direction, and the positive infinity tells us that the arrow is pointing to the right. Okay. So a linear function is a function that when you graph it, it's going to look like a line, a straight line, and it has a constant rate of change. Just like when we were looking at that constant rate of change previously, we had a graph up of a line that was a linear function. Now, a linear model is a linear function that's going to represent real life data. When you get into statistics, you may have some set of data points that are just kind of all over the place if we have this on a graph. Well, you'll be asked to graph or come up with a best fit line that would go through and be the closest to representing all those points. So it would represent the real life data that was collected, a linear model. So use linear models when you're talking about profits. How many people do you need to maintain based on how many customers come in? How much profit do you make when you sell things at certain prices? Because there's going to be a point in the profit where you no longer, the price is too high, and so your profit goes away because less people buy it. So you have to be able to determine these things, and we use linear modeling to represent that real life data to help us make those decisions. Ordered pair. Now, ordered pair comes from when you have a Cartesian plane or an XY coordinate plane here. You know, we have the x-axis and the y-axis. So if there's a point on here, let's say this point is right here, it's going to be to represent where on the plane this dot is, we have to put some numbers in. And so you put the X first, or the spot, it's horizontal spot in space first. So this is 2 over. So we're going to put a 2 there, and it is 4 up. So it's a positive 4. If we had that same point on this side, it would be negative 2, positive 4. So if you move to the right, it's positive. If you move to the left, it's going to be negative. Well, what happens when it's down here? Well, that's going to be negative 2 and negative 4. Okay, so the up on the Y, on the vertical, is positive, and the down is negative. And then that same point over here is going to be a positive 2, negative 4. If you see the pattern, we have positive, positive, negative, positive, negative, negative, and then positive, negative. And it's going to be the same for every point in that quadrant. Each section, each square, each part that's separated out by these axes is called a quadrant. So every quadrant 1, 2, 3, and 4, each quadrant has its own characteristics of positive and negative, no matter what the point is. All right, range. We talked about domain being all the values of X that are possible. Range is all the possibilities of Y, or the output. So I always hear it, domain and range. And you can remember that because you always hear it X and Y. So range is the Y value possibilities, and domain is the X value possibilities. And also, same as this, you hear input and output. Okay, so X is the input, generally speaking. Remember, our variables can change. We're not locked into X and Y. This is just the most common. And Y is the output. Okay, so those are the main things you need to remember: input and output versus X and Y, because those can always change. All right, slope. Slope is when we're talking about the constant change. It is the ratio of vertical change to the horizontal change between 2 points on a line. So we have the vertical change in y over change in x. That's what ratio means. Ratio means creating a fraction or a division symbol in this case. So you could have, I think one of them we looked at was 2 over 1. So we divided that and became 2. Another one we looked at was 4 over 2. So that became 1/2. Okay, so we just reduced that one. This one we divided, or you can also call that being reduced. But it always starts out as a ratio, the vertical change over the horizontal change, or the change in y over the change in x. And its slope is always indicated with an m. M is our label for slope. All right. Substitution. Substitution means that we're going to replace one element of a mathematical equation with another. So if we go back to that f of x that we had that equaled x squared, when I put in f of 2, I substituted 2 for everywhere that the x was. So I got 2 squared. So my f of 2 became 4. So substitution, just like in sports, if you have an injured player, you need a substitute. You need someone to tag in. You need someone to come in their place. And so that's what's happening here. We have 2 is substituting for the x. It's coming in its place. X-intercept. When we had a graph, the x-intercept is going to be the point on a graph where the line meets or crosses the x-axis. So first you need to know where the x-axis is, okay? Now you can have, we talked about linear graphs. This has one x-intercept, right? Well, most of the time with parabolas, you're going to have 2 x-intercepts. 2 places where the graph crosses the x-axis. It is possible to have a parabola. I did not draw that very well. That looks more like a V, but it's possible to have a parabola where there's only one x-intercept, or even 0 x-intercepts. It could be above the line and never touch it at all. So the x-intercept is the point on a graph where the line meets or crosses the x-axis. Sometimes these are called the zeros. Find the zeros. Why? Because if you plug, what would you plug in for x to find out what this point is? Well, you'd plug in a 0 to the y, and because the y doesn't move up and down, it's going to only be on the x. So if it equals 0, so say you had x squared equals 0, to find that x, that's how you find the x-axis, and that's why it's called zeros. So x-intercepts are also called zeros. Sometimes you're asked just to solve, find the solution. Sometimes you're asked to find the root, okay? So the roots, the solutions, the zeros, these all refer to the x-intercepts. Y-intercept are very similar, and yet just a little bit different. Remember, this was our x-axis. Well, here is our y-axis. So what do you think the y-intercept is? The y-intercept is where a line crosses the y-axis. That one doesn't have any special names that I'm aware of. That is all of our vocabulary for Unit 2. And hope to see you in the next video, Lesson 2.